Okay, we are finally finished with polynomials. Felt like we were on those forever. And now we get to move into rational equations and inequalities. If you remember from Algebra 2, we did rationals. It's probably my least favorite unit in everything that I teach because they are polynomials, sort of, but they are polynomials built into fractions, and most of the time you guys hate fractions. I love fractions, but y'all hate them, and so it's a struggle, and so I hate them. But it's okay because we did this in Algebra 2, so you guys should have a certain level of comfort with it and be a little bit okay. So here we go. The graph of this rational function, now it's considered rational function, remember, because the word rational has the root word ratio, and a ratio is a fraction, a comparison of one number over another. So in this case, I have one polynomial over another polynomial. So this is a ratio, so we call it a rational function. Here it is, pictured at the right. And then it's asking us to use the graph to identify the values for which the following equations or inequalities are true. So where does this equal 0? Only one spot here on the graph where it equals 0. You can see it right here. At x equals -1. This is a little bit of review of all the stuff we've been doing since the beginning of the year. Where is the function greater than 0? Notice it does not say greater than or equal to. It just says greater than, which means no brackets here. So now, notice here I have this little hole. So even though this is all greater than, I got a hole there, which means when I write this interval notation, I've got to stop there. So it's going to go from -infinity to the hole, which is at -3. It starts over immediately after that hole and goes from -3 to the x-axis, because at the x-axis it equals 0, right there at -1. And then the last place, this whole piece on the right-hand side is greater than the x-axis, or greater than 0. So that's from the asymptote at 1 all the way to infinity. All of these are brackets because it said greater than, not greater than or equal to, and because that's an asymptote. You can't touch an asymptote. Alright, so then it asks, where is it less than 0? Well, everywhere else, which is just this one little strip from -1 to the asymptote, which is at 1. Alright, so 4 and 5, the only difference between 2 and 4 is the bracket, because this has an equal sign underneath it. So I'm going to go -infinity to -3 at the hole. That's still a parentheses because that's a hole. There's nothing there. From -3 to -1. Now right here at -1, we highlighted that. It actually equals 0, so that gets to be a bracket right there. In union with, right after the 1, it starts over. Now since we put a bracket right here, oh wait, it doesn't start, that's below, over here. This is the asymptote. It cannot touch that asymptote at 1. It's never going to touch 1. So that's going to be a parentheses 1 to infinity. So that changed only one tiny little thing. It just made a bracket right there at 1 where it equals. And then it asked me where it's less than. Well, it equals at 1 right there. So that's going to be at -1, sorry. At -1, it's a bracket. To 1, which is an asymptote, so that's a parentheses. Okay, so that's kind of a review, just being able to read the graph. So given the function that they gave us, find the function values of g of -3 and g of 1. Show your work. Now, of course, you could go up to g of -3, and you can see right after that there's a hole there. But they want us to prove there's a hole there by plugging in the x value. So let's do that. It did say show your work, so let's make sure we show our work here. So I'm going to say g of -3, and that just means to plug in -3 everywhere there's an x in this problem. Simplify. 9 minus 12 is negative 3 plus 3. That's 0 on top. 9 minus 6 is 3 minus 3. That's 0 on bottom. It doesn't matter that 0 is divided by 0. That does not give you 1 because you can't ever divide by 0. So this is undefined. Because we're trying to divide by 0 right there. You can't do that. Alright, so let's do g of 1. Show your work. So this time I'm plugging 1 in for every x. Plus 4 plus 3, 1 plus 2 minus 3, that's 8 over 0. Undefined. You can never divide by 0. Using the graph above, explain why your efforts to find these things had the outcome that they did. Well, if we look at the graph, at x equals negative 3, there is a hole. Remember, now hole is just the slang term for it. It is actually a point discontinuity. You remember that from the beginning of the year? Or we called them removable discontinuities last year. Now, if you remember how you find a hole, if we were to take our original function, when we first got the function, and we were to factor it, do you remember how we identify a hole? If I factor this, it's going to factor as x plus 1, x plus 3 over x minus 1, x plus 3. Now, right there, x plus 3 and x plus 3. Now, I know what you want to do. You want to cancel it. But right now, that's not what we're doing. We're just identifying the fact that x plus 3 over x plus 3 is the same. That is how you identify a hole. What about, though, the G1? Where does that come from? G of 1 is an asymptote. Now, after we factored and we identified that as a hole, that left this piece remaining on bottom. And remember, the bottom can never equal 0. So x minus 1 equals 0. It gives you x equals 1, and that can't happen. That's an asymptote. So if you remember back to, we did a page in Algebra 2 called Remove the Bowl. And that's when we identified the holes. So you factor, identify the hole, and then you recognize that whatever's left in the denominator is going to be your vertical asymptote. Okay, so it says completely factor the function. We already did that. We did it right up here. Identify the values that make the function equal to 0 and the values which make the function undefined. So we want to find when the numerator is 0, but not the denominator. The denominator cannot equal 0. We already know those two places where g of x is undefined. We found them already, right here at these two places. It is undefined at x equals 1 because that is an asymptote. It is also undefined at x equals negative 3 because that is a hole. And you have to be able to identify which one is which, but they are both undefined. So we know that piece. Now we just need to know where g of x equals 0. We looked at that earlier. We know where it equals 0 because we did the, we looked at it at the very top. We know it equals 0 at negative 1, but we want to see how we can get there from this equation. Well, we've already factored it. we've already identified this particular piece as being a whole, which means what's remaining on top is what gives us our g of x equals 0. We want the numerator to equal 0. So because that is already taken up being a piece of the whole, I do x plus 1 equals 0, and I get x equals negative 1. Alright, so that is just a quick review of some of the things about rational expressions. We are going to work with rational inequalities first, and in order to work with rational inequalities, you have to know a little bit about rational expressions. You do, because we did them in Algebra 2. So, here we go. To solve rational inequalities, the process to follow is identical to the process we've previously learned to solve polynomial inequalities. That's why we're doing this right now. It goes with polynomial inequalities. You'll start to recognize it when we start. In the case of rational inequalities, we must not only divide the number line into the pieces used for sign analysis that make the function equal to 0, but we also have to consider the pieces that make the function undefined. So, your first step every time is going to be to completely factor the rational function. So let's factor. This factors as x plus 3, x plus 1, and over x plus 3, x minus 1. Yes, this is the one we just did, but we did not do it as an inequality. We did it as a function. So now we're doing it as an inequality. Now, step number 2. Set each factor equal to 0 and find the zeros of the function and where the function is undefined. Now, we did this on the previous page, but just so you know what we're doing, x plus 3 equals 0, that's here. X plus 1 equals 0. X plus 3 I've already written, so you don't have to write it twice. And then x minus 1 equals 0. So x equals negative 3, x equals negative 1, and x equals 1. Alright, draw a number line that is divided into segments with these zeros. So, negative 3, negative 1, and 1. Now we are going to choose a number from each interval and determine the sign for each factor based on the chosen value. So we've done this before. You don't even really have to calculate. We just want to figure each piece. So if you notice, in your factored equation, I'm going to have 1, 2, 3, 4 pieces each time. So let's choose a number to the left of negative 3. So let's just say negative 4. If I plug negative 4 right here, that piece is going to come out negative. If I plug negative 4 here, that piece is going to come out negative. Here it will be negative, and here it will be negative. Negative over a negative would be a positive. A negative over a negative is a positive. That makes this entire section positive. Alright, let's do it again. Between negative 3 and negative 1. So let's go with negative 2. That makes sense right there, doesn't it? So if I plug a negative 2 right here, that first top piece is going to turn out positive. If I plug a negative 2 right here, the second piece comes out negative. If I plug a negative 2 right here with that x plus 3, that piece comes out positive. If I plug a negative 2 right here, this piece comes out negative. Alright, positive and negative on top means the top is negative, the bottom is negative. That makes this entire piece positive. A negative over negative becomes a positive. Alright, let's go right here between the two. Well, between negative 1 and 1 is 0, so that's easy. If I plug a 0 on top, that's going to be a positive piece. That will be a positive piece. This will be positive. But right here, that's going to be negative. the top would be positive, the bottom would be negative. That makes this whole section negative. One more. To the right of 1, let's just use 2. So let's see, my first piece would be a positive piece. Positive, positive, positive. This whole thing is positive. So I only have one little negative section right there. Okay, so it says refer to the original inequality. In this particular example, the inequality sign is less than or equal to 0, which means the solution will be the values that make the polynomial negative, where it is negative, which is right here. Write the solution intervals. Now, here's where you have to be a little bit careful, because I do have less than or equal to sign, which means I could potentially have brackets, but I have to keep track of what was an asymptote and what was not an asymptote, because asymptotes can't ever have brackets. So if you remember, this was our whole, this is our asymptote, but this piece right here is actually your 0. So this whole section is negative. So that's my answer, because that's where this function is less than 0. So when I write it, this piece was not an asymptote, so I can put a bracket. So negative 1 to 1, but because 1 was our asymptote, that's going to have to be parentheses. Now if you look, I had the function, so x squared plus 4x plus 3 over x squared plus 2x minus 3 needed to be less than or equal to 0, or g of x needed to be less than or equal to 0. Well, if you look at the graph, that is this piece right here. So the function needed to be less than 0, and that's this piece, which is exactly what we found analytically. All right, so let's try again. Now, step number 1 says completely factor the given rational function. How nice of them. They completely factored it for us. So they want us to set each factor equal to 0. So x plus 3 equals 0, x minus 1 equals 0, and x plus 2 equals 0. Even though it's a double root, you don't have to do it twice. So x is going to be negative 3. 1, and negative 2. Set up your number line. So I set each factor equal to 0. I found the zeros of the function and the values where the function is undefined. It's undefined here because that's on bottom. So that's your asymptote right there. Draw my number line. Divide it into segments. Make sure that you get them in the right place. So negative 3 comes first, then negative 2, and then 1. Now we're going to choose a number from each interval, plug it into the original factors, and determine whether this will be positive or negative. Now, I'm going to choose negative 4 for this first area over here. Plug a negative 4 in that top piece, and it'll be negative. Second piece will be negative. The bottom piece would be negative. Negative 4 plus 2 is negative 2, but you're going to square it. So it'll be positive. A negative and a negative makes a positive, so I end up with a positive over a positive, which makes this whole piece positive. Between negative 3 and negative 2, we could say negative 2.5. If I plug that into the top piece, the first left corner piece will be positive. Second piece will be negative. On the bottom, it would come out negative, but you square it, so it's going to be positive. That ends up a negative over a positive, which makes this whole piece negative. Alright, between 2 and 1, that's where 0 falls. So that's an easy enough piece. The top piece will be positive, negative, over a positive. So I end up with a negative over a positive, which makes this whole thing negative again. And then let's go to the right of 1, we can use 2. It'll be positive, positive, positive. So this whole thing's positive. Okay? Now refer to the original inequality sign. Well, my original inequality is less than 0. Just less than. No bracket this time because it's not equal to. So it is less than right here. But do notice, there's a reason why it's split into 2 intervals. So when you write this, you must write 2 separate intervals. From -3 to -2 in union with -2 to 1. I don't really have to concern myself this time over what is an asymptote and what is not because it was just less than. So there's not going to be any brackets anyway. So less than, so this is my function. Let's just say that it's f of x. They're saying f of x needs to be less than 0. So my function had to be less than 0. If I look on my graph where that takes place, that would be from here to here and then again right here. And that is exactly from -3 to -2 where there is an asymptote. From -2 to 1. Again, no brackets because it just said less than. Okay, just a couple more to practice. At the top of the page it says solve each of the rational inequalities and show your complete sign analysis. Check your solution on your graphing calculator. Now, remember, we're supposed to be factoring these completely. But I have a little problem with this first one on the left-hand side. It doesn't factor. So instead of factoring, I am going to have to plug it into the quadratic formula. So let's plug that into the quadratic formula. Let's see. Quadratic formula is -b plus or minus the square root b squared minus 4 is all over 2a. Okay, so -4 plus or minus the square root of 16 minus 4 times 1 times 2 over 2. Simplify that. It's -4 plus or minus 2 square root 2 over 2, which is -1 plus or minus square root of 2. Now here's the problem with that. There's nothing wrong with that answer. That's actually a correct answer. But I don't have any idea where that is on a number line. So it did say, check your solution on your graphing calculator. Since it said that, let's go ahead and plug that into our calculator and get actual numbers. Because remember, we have to put these on a number line. And if I don't know where it is, I can't put it on a number line. So let's see. Alright, so I get x equals 0.414 and -2.414. And don't forget, we also are concerned with the top factor, x minus 3. So I know x also equals 3. So I can put this on a number line. So I've got -2.414, and then 3. We've got to check each region here. So I'm going to check to the left of -2.4. You know what, I just realized I did that wrong, because when I simplified, I didn't simplify correctly. And I know y'all are probably already freaking out, but since you're not here, okay, I knew something was wrong. Okay, hold on. 2. I'm probably trying to figure out what I was doing. Crazy woman. Okay. -5.86. Okay. -0.586. Sorry. -0.586. Bigger 0.414. And then 3. Okay, so let me fix my number line real quick. So this is going to be negative 3.414. This one is going to be negative 0.586. This is why I shouldn't do math in pen, but y'all can't see pencil when I write up here. So, okay, and then 3. That's in the right place. Okay, so now we got to check our intervals. So if I am going to plug a negative, so let's just go with negative 4. If I plug a negative 4 up here, that top number is going to be positive. The middle, if I plug in a negative 4 here, square it, plus 4 times 4, that's just 0, but that's a positive. So it's a positive over a positive. Should be. Why did I say that? I said negative. This is negative. It's a negative over a positive, which makes this whole section negative. Alright, between these two, doesn't really matter what number you use, so let's just use negative 1, because negative 1 would be over here. That top piece would be negative. The middle piece, 1 squared is 1, minus 4 would be minus 3. So that's a negative over a negative, which makes this section positive. 0 falls in here, so that makes the top piece negative and the bottom piece positive, so this whole section is negative. And then greater than 3, let's do 4. That's going to be a positive over a positive, which makes this a positive. Alright, so we're looking for where it's greater than or equal to 0, because I refer to the original sign, greater than or equal to. That would be my sections that it's positive. Now I do have to take into account what my asymptotes are. My asymptotes are my weird numbers, because they come from the denominator, remember, in division factor, so that's where I got those weird decimals. So these two values are asymptotes. This value is an actual 0, so it can have a bracket. So I'm writing the interval where it's positive, because that's greater than. So it's going to be positive from parentheses, negative 3.414, to negative 0.586, close parentheses, in union with this section, which will get a bracket, because that's not an asymptote, to infinity. Alright. This one's going to be a little easier because it's already factored for us. So you just have to find your zeros. So 2x plus 1 equals 0, x minus 3 equals 0, and x plus 2 equals 0. So x equals negative 1/2, x equals 3, and x equals negative 2. Set up your number line. Negative 2, negative 1/2, and 3. You're going to check each region and see what kind of sign you end up having. So let's go left of negative 2, negative 3. We can plug that right there. That would make that top piece negative. It would make your middle piece negative, but you square it, so it's going to be positive no matter what. Same thing for the bottom. Kind of makes this easy. Plug in a value between these two. We could go negative 1 here. If I plug that in the top, it's going to be negative, but the other two are going to be positive because you square them. That makes this piece negative. In between these two would be 0. So that's going to be positive, positive, positive. And if you go this way, it's also going to be positive, positive, positive. Checking my original sign, I'm looking for where it's less than 0. That is these two places. I don't have to concern myself with brackets or not, but you do have to concern yourself with the fact that there's a reason why it is written in 2 intervals. So you must write it in 2 intervals. From negative infinity to negative 2 in union with negative 2 to negative 1/2. Alright, so now this one looks a little bit crazy and messy. But it's actually not, it's going to be the same type of problem. What we're going to do first is move this over so that we can set our inequality sign less than or equal to 0. And then it'll be like we're used to. So 3 over x plus 2 minus 2 over x minus 1 is less than or equal to 0. Now, we've got to combine these two, make it all one term, because currently it's 2. And this is why y'all don't like rational expressions. because in order to combine fractions, you have to have a common denominator. Now, if you remember way back into Algebra 2, in order to have a common denominator with rational expressions, you cannot remove pieces from the denominator. You can only add pieces too. You remember Fred and Ted? Remember Fred had a hat and Ted had a bow tie, and Fred had a goatee and Ted had glasses. You couldn't take anything off of one, you could only add pieces. Well, x plus 2 is a piece. It goes all together. X minus 1 is a piece. So each fraction has to have each of these pieces. So this fraction is missing the x plus 2 piece. So, the x plus 1, the x minus 1 piece. So if I put x minus 1 on bottom, I have to put an x minus 1 on top. This fraction is missing the x plus 2 piece. If I'm going to put an x plus 2 piece, I have to put it on both top and bottom. Alright, so let me write that out so just a little bit more clear. I have an x minus 1 that I'm putting on top because I put 1 on bottom. So that's this piece minus, and this piece I put an x plus 2 on top because I put 1 on bottom. Alright, so we're going to go ahead and distribute. Now, do not FOIL out the bottom, because we're going to go back and factor it anyway. But the top we have to do because we might have like terms we can combine. So 3x minus 3. I'm going to go ahead and distribute a negative 2 here. Minus 2x minus 4. It is now all over the common denominator. So if I simplify on top, I get x minus 7 over x plus 2, x minus 1. That is a whole lot easier to deal with. Now I've got factors and things I can recognize. Set each factor equal to 0. X minus 7 is 0. X plus 2 is 0. X minus 1 is 0. Recognize these two pieces as your asymptotes. So this is x equals 7, x equals negative 2, and x equals 1. Set up your number line. We're going to check something from each region. Plugging it into this equation, the one that we simplified right here. Alright, so I'm going to go negative 4 here. That would make the top piece negative. I don't know why I chose 4, but I just did. That would make this one negative, and this one negative. Well, negative over negative is a positive, so this whole piece is positive. Between negative 2 and 1 is a 0. If I plug in 0, the top piece is negative. The bottom left piece is positive, bottom left right piece is negative. That's a negative over negative, which makes this whole piece positive. You know what? I missed this because this is a negative. Oh! Negative 4. Right, that makes this negative. That's negative. That's negative. So this is negative. Whew. Okay. Sorry. Okay, between 1 and 7, let's go. 6. Top piece would be negative. Positive, positive. That makes this whole section negative. And let's use 10. 10 is to the right of 7. That would be positive, positive, positive. So this is positive. Okay, so this one goes negative, positive, negative, positive. I am looking for where it is less than or equal to 0. So remember, I told you we've got to identify our asymptotes because asymptotes can't ever have brackets. So when I'm going less than or equal to, that's these pieces. I just have to make sure I don't put brackets on an asymptote. So I go parentheses in negative infinity to negative 2, which is an asymptote, so that's a parentheses. And union with 1 is a parentheses because that's an asymptote, to 7 bracket because this has an equal sign, and 7 is not an asymptote. Alright, so there you go. That is all for today. You will do the assignment tomorrow.